Okay, next let's look at the show interface status. Okay, on the 5Ks we can see we have our 32 ports that are built in. So E1 through E32. This is because this particular platform is a 5548 UP, which again means that it has 32 fixed ports, and it has an additional 16 ports that are available for the expansion module. But now also when we look at the show interface status, we see that we have the fabric extender, which is now denoted as the E101 module. So E101/1/1, this means that this is the first port on the 32 ports of the extender that we have facing downstream. The other interface that we had configured, E110, if we look at the show interface E110, E110 brief, it says the mode is running in fabric. This means that this is connected to a fabric extender on the other end, or in other words, we're running the VN tag protocol on this particular port. Now, the rest of the configuration of the extender is going to be the same as if these were locally attached interfaces. The only difference is that from a physical layer 1 wiring point of view, it's simplifying our runs from the top of the rack to the end of the row. So in this particular case, we're only using one fabric port, which means that if we physically wired the 2K top of rack to the end of the row, it means that we would only have one run that we would need to go to this particular parent switch. Now, in most real designs, you would probably use multiple uplink interfaces though, both for the point of redundancy and for bandwidth availability. Because as we talked about with the physical wiring of the FEXs, one of the potential disadvantages of this design is that if we have 32 server pacing ports downstream on the FEX, so this is for our 22, 32 PP, and we have 8 uplink ports facing towards the parent. So if we're going to our 5548 here, what's going to be the potential issue of the servers that are physically connecting to these interfaces? So if we have A, B, C, and D that are all running as 10 gig, as long as we have at least 4 uplinks going northbound, then each of the servers should be able to get line rate forwarding. But if we have less than that, let's say that out of our 8 possible uplinks, we're only using 2 of these, it basically means that we have a ratio of 4:2, or in other words, a 2:1 oversubscription ratio, because when the servers actually go to access the backplane is based on the number of physical uplinks that we're using from the extender to the parent switch. So just like in the case we saw with the 7Ks, the different ports are assigned to different port groupings, which controls their ASIC access to the fabric. In the case of the fabric extenders, it's going to be those physical cables that are uplinking us from the 2K to the 5K or the 2K to the 7K. They control how much bandwidth access do we have to the fabric. Now, from a physical design point of view, when we go to plug the fabric extender in, there's a number of different ways that we can set this up. Okay, the simplest way would be if we have a single attached server going to a single attached extender. So if we have the 2K physically plug one cable to the 5K, and then we have one cable going down to the server. That's basically what we have in this design, but what would be the disadvantage of this? Disadvantage is that the server is single attached, so if their physical NIC goes down, the server loses connectivity. If the cable between them and the extender goes down, if the extender goes down, if the link from the extender to the parent switch, or if the parent switch goes down, basically we have lots of single points of failure in this case. So we have one point of failure for the parent switch, another one for the uplink, a third one for the extender, a fourth one for the access cable, and then a fifth one for the actual NIC card that the server has physically plugged in. So in most realistic designs, you probably don't want the server singly attached, assuming you want some sort of high availability in the environment. So the other option is that we're going to dual attach the server to multiple extenders. So instead of having just one parent switch upstream, we're going to have the network look like this, where we have 5K1 that is connected to 2K1, and then connected down to the server. Then we have 5K2 that is connected down to a second extender that is then connected dual attached to the server. Now, in this type of design, we have two different options from the server's point of view, whether we want to do active standby forwarding or whether we want to configure the links as a port channel. Now, ultimately, this decision is mainly going to be up to the OS level of the server and how it has the option to do different types of load balancing from the either the NIC card or from the OS that's running. So let's say, for example, that we're running ESXi on the server. So we're running VMware as the hypervisor, and we have a couple different virtual machines. We have virtual machine 1, we have virtual machine 2, and so on and so forth. Now, from ESXi's point of view, it has the ability, it has the intelligence to say that I'm going to take virtual machine 1 and I'm going to assign it to this uplink, and I'm going to take virtual machine 2 and I'm going to assign it to that uplink. So basically, we would have active forwarding, but on a per virtual machine basis. Now, we could also say, well, let's not let the OS level do this. We're going to do this from the network point of view. And the way that we do that is to configure the links as a port channel. So the third option would be very similar to what we have here, with the difference being that what we would need to do is to have some sort of communication between the access switches, which in this case are the 5Ks, in order to deal with that channel that's going down to the server. Now, we're going to take a look at this in much more detail later when we get into the specifics of this technology, but this is what we would consider to be a virtual port channel. Now, a virtual port channel, so in this case we would have these switches cross-connected, and then we would configure a port channel on this interface here, or specifically what we call a VPC, a virtual port channel. Now, a virtual port channel is similar to, in the Catalyst world, what we call VSS, the virtual switching system, or in the access layer Catalyst, like 3750, what we call stackwise. Now, in the case of a stackwise system, we have multiple fixed access switches like 3750X that we connect on the back end with a special stacking cable that extends the backplane between the switches. So ultimately, what the end result of this is that if we take our server and we plug the server into 3750X1 and 3750X2, then between these, we're running the stack cable. On the server side, we configure this as a port channel. Okay, we configure that as an ether channel. The end result from the server's point of view is they think the network looks like this. That we have the server downstream and then we have one physical switch upstream. Because from the stackwise point of view, it behaves like a modular chassis. That even though they're two separate physical switches, we're basically clustering them together. So the downstream device doesn't know that there's multiple upstream switches that they are physically connecting to. Okay, the same would be true if these were Catalyst 6500. So let's say these are 6509s. And in the case of 6509, we would be running this as a virtual switching system, or a VSS. So between those two switches, we would be running a virtual switch link, or what we call a VSL. The VSL basically clusters the 6500s together. So the end result is that the server sees this same type of topology. Now, in the case of the Nexus world, this would be if we have, let's say, 5K1 and we have 5K2. And between these, we're running the virtual port channel feature. The end result is that from the downstream server's point of view, they think that they're connected to only one physical switch upstream. Now we'll see from a specific implementation point of view, the VPC configuration works differently than the stackwise or the VSS config, but the end logical design is the same. That we're taking multiple physical switches and we're clustering them together in order for them to behave like one switch as we're sending the traffic downstream. Now what this means from a fabric extender point of view is that we have a couple additional supported topologies depending on what the northbound parent switch is. So if we have the 7Ks northbound, we can have 7K1 and 7K2 running as a virtual port channel domain. We then would connect the 7K1 down to the fabric extender, so this would be 2K1, and 7K2 connects down to 2K2, and then we can go down to the server as dual attached. So from the server's point of view, they're going to configure this as a port channel here, and from a logical point of view, they're going to see just one upstream switch, and they have a port channel that's going to that one logical switch. In the case of the 5Ks would be able to support this same design, but they also are able to support another variation, which looks like this, where we have 5K1, 5K2 that are in a VPC, okay, they're in a virtual port channel. We go down to the fabric extenders. The fabric extenders go down to the server, and from the server's point of view, we configure this as a VPC. So these are identical designs between the 5K and the 7K, but the alternate one that the 5Ks also support is to interconnect the fabric extenders in a diagonal as well. So we essentially have a full mesh of connectivity from the top of rack switches to the end of the row. So we have end of row switch 1, we have end of row switch 2. We connect them in both directions, and then we configure the links to the server as a port channel, and we also configure the links that go from the extenders up to the parent switches as a port channel. This specific design is called an enhanced VPC. So it's a virtual port channel that goes from the parent switch down to the extender, and it's a port channel that goes from the extender down to the server. But from the server's point of view, it still looks like a logical connection to only one upstream switch. Now we'll see from a configuration point of view, there are going to be some other design considerations we need to take into account. Because when we configure 5K1, and if the configuration is different on 5K2, they're not going to be able to agree on how do they channel down to the final destination. So we'll see specifically when we implement this, there's a bunch of control plane that we need to set up on the back end in order to make sure that the switches synchronize the information with each other first, like the MAC address table, the ARP cache, the IGMP snooping cache, that all needs to agree between the two switches, because otherwise we may not be able to forward traffic to the end host properly. So we'll come back in a separate section to talk about the details of virtual port channel, but the point being for this case with the fabric extender is that we can have single attachments that go up to one parent switch, which again is going to be the one on all the way on the left here. But as we can see with this, there's 5 different potential single points of failure. Single point of failure of the parent switch, of the link to the FEX, of the FEX itself, the FEX link down to the server, or the server's NIC card. Okay, now if we were to go to multiple parent switches and we run as active standby. In this case, the parent switches are not running in a virtual port channel. This is just up to the server's operating system to choose which of the links are we going to send the traffic out. So it's not configured as a port channel. It's just where we have multiple trunk links or multiple access ports going down to the server, and then the server is doing the load balancing at the OS level. Where this is typically where you would see VMware in the vSwitch choosing what particular uplink the VM NIC that the traffic is going from the VM northbound. Okay, then the third option is we have the virtual port channel. So we have the server plugged into multiple top of rack switches. The top of rack switches, so this is where we have the top of rack. Then the 5Ks are at the end of the row. So these are the runs that are going between the cages, and we have each of the top of rack switches plugged into one of the parents. So in this particular design, if the NIC goes down, if the link between the server and the extender goes down, if the FEX goes down, if the link between the top of the rack to the end of the row goes down, or if the parent switch goes down, we can now survive any of these 5 failures because we can always go to the alternate direction. In the case of the enhanced VPC, we have even more directions that we can go. So if these links go down, we can go that direction. Okay, and so on and so forth. So based on the port channel load balancing method, we have lots of access on the fabric bandwidth that we're going to the backplane of the 5Ks. So we're essentially taking what was oversubscribed bandwidth down to the server ports, and we're trying to load balance this between multiple upstream parent switches. So we're not doing as much contention on a per port basis for the fabric bandwidth. Now, as you can imagine, though, one of the disadvantages of this is the number of wires that you need to run. So we're increasing the runs from the top of the rack to the end of the row, but we're also increasing the management complexity because 5K1 and 5K2, they're 2 separate switches that have 2 independent management and control planes. And we'll talk about this in more detail a little bit later in VPC, but one of the big differences between the VSS, the Stackwise, and the virtual port channel is that in both Stackwise and VSS, there is one single control plane. This means that if you telnet to one of the members of the stack, you always land on the stack master. So you look at the configuration, it's automatically synchronized between all of the members in the 3750 stack. The same is true of the VSS. When you telnet or SSH into the VSS management interface, you're controlling both of the switches at the same time. But in the case of virtual port channel, it's 2 independent control planes, 2 independent management planes. This means that you need to manually make sure that the configuration is 100% synchronized between the parent switches. Otherwise, there ends up to be data plane forwarding issues as you go down to the end host, to the end server. So we'll see that specifically when we look at the VPC config, but it is something to take into account in the design. If you do this last option, which is the enhanced VPC, generally you need some sort of like configuration management to make sure that they synchronize their configurations. Now, as someone had asked the question here, is there a sync command? There is a feature to do it automatically, but it doesn't work very well. So there's not that many people that I know that use it in production because it's a very limited, it's a very finicky feature. What it is specifically called, if you look at the Nexus 5K documentation, it is under system management. It is called configuring switch profiles. So switch profiles, basically, you configure a profile on each of them. You make your configuration changes on one, it synchronizes to the other, and then it downloads the config to the port at the same time. So it's supposed to work in theory, but when you try it out in production, it's really not that stable of a feature. So in most implementations I've seen of this, you just make sure to manually make the config equal on both sides. So like you take your template and you just paste it on both switches at the same time to make sure that the server-facing port has the same final config. Okay, so let's go back to the CLI here, and let's look at the end result of this with the fabric extender. So as you can see, the configuration for this is very, very straightforward. There's only 3 commands that I had used so far. If we look at the show run, include FEX. Globally, I said feature FEX. That's turning it on. Then under the port level, this is under interface E110, I said the switch port mode is FEX fabric. What this is doing is turning on that VN tag protocol. Then I'm saying the FEX associate number is 101. This means that all of the ports E11 through E132 on the FEX are going to show up as E10111 through E101-132. So as long as this number is unique for all of the FEXs that are associated to that parent switch, the number is essentially arbitrary. Now, from a documentation point of view, you would probably want to know this. You would know you would want to know which top of rack switches have which associate numbers, because that ultimately affects how you configure the interfaces that go towards the servers. So there are some additional protection mechanisms that you can add and that you normally would for best practices, where in the case of the global config, if you go under the FEX mode, you can specify what is the serial number of the FEX that you will allow to associate on that particular port. And what this does is to help you when you're doing the physical wiring in the data center, because when you do the long run from the top of the rack to the end of the row, you might not be sure what uplink that you're actually supposed to plug it in. So with this configuration, it's basically a protection mechanism. It's a protection mechanism to say that if someone physically wires the ports wrong, I'm going to know because it's the wrong serial number of the fabric extender. The other option that's very useful from an operations point of view is that if you are remotely configuring the box and you have someone in the data center that's doing physical wiring, you can go to the port number and you can turn on the beacon. Okay, what this feature does is there's a little LED light on the actual port that starts to flash when you turn the beacon on. So you say to your data center operations person, look at the port that's flashing. That's where I want you to plug the cable in. So then if you're trying to do troubleshooting and you have this huge bundle of cables that's long distance runs between the cages, then it makes it a little bit easier to correlate the physical layer 1 network and the logical configuration that you're actually applying onto the interfaces. Okay, but beyond this, when we look at the configuration of the ports that actually go to the extenders, this is going to behave as just a regular layer 2 Ethernet port. So if we look at the show interface E10111 switch port, it says that switch port is enabled, which means that this is a layer 2 port. Right now, the operational mode is access. The access VLAN is 1. Additionally, private VLANs are not configured. And if we look at the show spanning tree interface E10111 detail, for the fabric extender facing ports, or the server ports on the FEX, there's 2 features that are always enabled that you cannot turn off. Well, technically 3 features. Okay, one of them is that the port type is configured as edge. In the Catalyst world, this is what we call port fast. The idea being is that whatever device you plug into the fabric extender, it should not be a switch. So you don't need to be running spanning tree on that particular port. Okay, additionally, since you're not supposed to be plugging switches in there, we're going to be filtering out bridge protocol data units, which basically is saying spanning tree hello packets. So we're going to filter spanning tree on the interface, and if we receive spanning tree on the interface, we're going to shut the port down. Okay, BPDU guard is a protection mechanism to make sure that no one plugs a switch into the interface because the fabric extender has spanning tree disabled. So if you were to connect a switch here, you could cause a layer 2 loop because one side's running spanning tree, the other side is not. So the protection mechanism there is just to say, if I receive a spanning tree hello inbound, I'm simply going to disable the interface. So from a physical wiring point of view, you're not allowed to plug other access switches into the fabric extenders. Now there are technically some workarounds for this, like you could disable spanning tree on whatever that access switch is that you plug into the FEX, but it is kind of a dangerous design that if you do create a layer 1 loop or a layer 2 loop, you can bring down the network through a broadcast storm or a high CPU utilization when there is a loop that cannot be caught by spanning tree. Okay, so as I mentioned, the FEX ports are going to be layer 2 spanning tree edge. This means that they don't have to wait for the spanning tree listening and learning delay. So when you boot up your server can immediately forward. It doesn't have to wait for spanning tree to converge. Then it also runs BPDU filter, runs BPDU guard. This means that if you do plug a switch in, it's automatically going to disable those ports. And you cannot turn these features off. Even if you put the command at the link level, it doesn't actually apply on the server-facing port.